Okay, I'm going to talk about Gauss's law. So Gauss's law is a way of calculating the electric field. And so just to quickly recap what the electric field is, right? So the electric field is a concept that helps us explain how charges can act at a distance, right? So one charge can exert a force on another when they're not touching. And so we see this kind of behavior from the electric force, from magnetism, and from gravity as well. Right, so this idea of a field is not something that's just specific to electric field, but it's a concept that really helps us describe forces that act at a distance without touching. And this was the issue, right, that Michael Faraday thought a lot about, because forces were really thought to be, to arise from contact before that. So how do you explain things that are exerting forces on one another without touching? Okay, so just to remind you, the electric field is showing you sort of the strength and the direction of a force that a positive test charge would feel. So the positive test charge does not affect the field at all, right? But we can bring it into locations around, for example, a positive charge, and that a little positive test charge is always going to get pushed away from that positive charge because the like charges repel each other. And then on the right here is the electric field, just to remind you what the negative charge looks like. Again, if we have a positive charge here, it's going to be drawn toward the negative charge, and as it gets closer and closer, the strength of the attraction is increasing. So that's the electric field. So it fills all of space, right? And it shows us the direction of the force and the strength of the force that a positive charge would feel at that point. Okay, so to lead into Gauss's law, let's think about these boxes. So we don't know what is inside the box, but we are able to see the electric field lines. So can you tell just from the electric field lines what is inside this box? So on the left here, we have a box that has electric field lines coming out of the box. In the middle, we have a box where there's electric field lines all flowing into the box. And then on the right, the electric fields are coming in one side and out the other, right? So there's something originating or ending in the box. And so based on what we just saw for electric field, we can tell that there must be a positive charge in here, right? Because we're seeing all the electric field lines diverging from inside this box. And there must be a negative charge in here because all the lines are converging. Right? So there must be a negative charge in there. And then here, there's probably no charge inside the box because the lines are just passing right through. These lines are originating from something else. Okay? And so this is the idea of Gauss's law, that we have, if we look at the flow of electric field lines in or outside a closed surface, into or out of a closed surface, then it tells us something about the charge that's inside. And so that's pretty much it. So, in official terms, it says that the electric flux passing through a closed surface is equal to the amount of charge enclosed by the surface. And that's it. So we're done. We can stop there, right? Unfortunately, it gets a little more complicated. So let's break that down, right? The first part of Gauss's law is about electric flux. So what does that mean, electric flux? It's the definition is it's the amount of electric field lines passing through a surface. And so this visual here is just trying to help you understand electric flux. The analogy is that you have a wire loop and you're holding it into the wind. So, and the flux then would be how much of the air is passing through the loop, right? Or maybe you're holding it in front of a fan. So if you're holding the loop kind of perpendicular to the way that the air is flowing, you're going to get a maximum amount of air flowing through the loop. And if we take the extreme other case, which when our loop is kind of the surface is parallel to the wind, you're not going to get any of the air flowing through that surface. So when we talk about electric flux, somehow we have to account for the fact, the relative direction, let's say, of the field and the surface. Okay. So like I just said, electric flux depends on the relative orientation of the surface and the field. So just to kind of break this down, we have when we talk about a particular area, we represent the direction with an area vector. And the vector points perpendicular to the surface, and the length of this vector is going to be equal to the area of the surface that it's representing. Okay, so this is a convenience that helps us calculate flux. And again, we could have an area that was a circle, for example, a little tiny circle, and the area vector would be perpendicular to that surface. Okay, and the reason that this helps us now is that we can think about if, let's say, we have electric field directed to the right, and we have this loop at or circular surface at some angle. We can now describe the angle between the area vector and the electric field. Okay, so that'll help us figure out what the flux is. Okay, so electric flux by definition is the dot product of the electric field times the area vector, which again is representing just how much area there is. And the dot product, you'll remember, so if we break that out, it's just the magnitude of the electric field, magnitude of the area, times the cosine of the angle between them. Okay, so if we look at this geometry here, if cosine is 0, that means that the circle will be perpendicular to the electric field and you get the maximum field lines through the loop. And then if we tip our surface over so that theta is 90 degrees, then we get back to the situation where the loop would be in this direction, parallel to the field, and you wouldn't get any flux through there. Okay, so mathematically that dot product is just helping us account for the relative orientation of that surface in the field. Okay, so let's just visualize that a little bit. Need a camera. So I have a wire loop, and I just drew field lines. Remember, we can use these lines to represent 3D. So we have x's, that's like the back of an arrow going into the page. Okay, so I made a little wire loop here, right? And if it's just sitting flat on the surface here, I can see 9 field lines going through the loop. And remember that the area vector is going to be perpendicular to this, right? So the area vector is like, 10 is too big. Something smaller. What this is, but the area vector is like perpendicular to this loop, right? It's coming out like that. Okay. All right, so now let's look at what happens to the number of field lines. And so the flux is just, let's count the number of field lines we got through here. So we have 9 field lines. Okay, so let's rotate this loop a little bit and see what happens to the number of field lines that we can see through the loop. So we start spinning. It takes a little while. Right? Okay, now we just lost the 2 edges, right? So now I see 1, 2, 3, 4, 5, 6, 7 lines through there. And if I spin some more, I'll drop those other 4, and I see 3 lines, field lines coming through my loop. And then if I go to the extreme, where my surface of my loop is perpendicular to the field, I won't get any lines through there. All right, so 3 lines, 7 lines, 9 lines, maybe one more. So we can have them up above. Oh, look how many we can get that way. Get a minimum of 9. Let's try it again from all the way up here. Whoa. Let's see the number of field lines dropping. Let's go here, let's go to 0. And then we can go the other way too. But that'll relate to motors a little more. Okay, too big. Okay, so that was fun. You get the idea, hopefully. Let's go back to our presentation. Okay. Okay, so Gauss's law in a nutshell. So if there is a net flux of electric field lines into or out of a closed surface, there must be a charge inside. And related to that, if there's no net electric flux, then there must be no enclosed charge. So conceptually, this is pretty straightforward. But mathematically, it's a little more complex. But we're going to stick to simple examples that actually make the math pretty easy. So, so a more quantitative way of expressing Gauss's law is electric flux through a closed surface is proportional to the amount of charge enclosed. So phi is our symbol for electric flux. Okay, this is integrating our electric field lines around the closed area, and this is the enclosed charge. Okay, So our charge will be in coulombs. Epsilon naught we've seen. We mentioned it briefly when we did Coulomb's law. It's another way of expressing the constant that goes with Coulomb's law. So we could say that, K is 4 pi over epsilon naught, or epsilon naught is 4 pi over K, where K is a Coulomb constant. That's 9 times 10 to the 9 Newton meter squared per Coulomb squared. Okay. So again, let's not be afraid of this. This is actually a surface integral. For those of you who've done Calc 3, saying that we have to sum our electric field over the entire closed surface. But we'll see that we can simplify that quite a bit if we choose our surfaces wisely. But first, let's just think about what this closed integral means. So, and the simplest thing to think about is just if I had the closed integral of an area element, and I wanted to integrate that around the surface of the sphere. We're not actually going to do the integration, we're just going to think about it, right? So it means if we look at this sphere, integration is all about like chopping things into little pieces and summing them up, right? So it just means that I have to take this little square, calculate the area, and then add it to that little square and that little square, or maybe I'm going around this way, however you want to do your sum. And you're going to sum all those little pieces up. And what you would get then is just the surface area of the sphere. Right, so if we did our closed loop integral of the area around the surface of the sphere, we would get 4 pi r squared. Okay. So just to review some other geometry that comes up frequently, right? For if you have circle, the black line here is showing our circumference, that's 2 pi r, and then the area is in gray here is pi r squared. For the sphere, the volume is 4/3 pi r cubed, and the surface area is 4 pi r squared that we just saw. So those are things that you should have at your fingertip. Okay, so what if we did our closed loop integral of area, but going around a cylinder? And we're going to assume that this is an open cylinder for now, because mostly we're going to deal with things that are infinitely long. So again, the concept is we're going to take all these little square blocks, calculate the area, and then sum them up. And so for cylinders, you usually want to envision that you're taking a strip right around here, right, that's got a length of this equal to the circumference of the cylinder, so that's 2 pi r. So that could be like just this top strip here. We calculate the area of that, and then we would multiply by the length of the cylinder. Okay, so it's our circumference here times the length. That would give us the surface area of the cylinder. Okay, so Gauss's law is very connected to the concept of symmetry. And symmetry just means that if we rotate an object about an axis or reflect it about the plane, it will look the same. So this is an example of a cylinder, and you can look at all the different ways that a cylinder has symmetry. So we can slide it along this axis and it wouldn't change, right? We could rotate it around this way, it's not going to change. You can like bisect it with a plane and reflect it that way, oops, and it won't change. Or even lengthwise, you could reflect it and it won't change. So cylinder has a lot of symmetry. Okay, and the symmetry of the electric field for any charge distribution has to match the symmetry of the charge. So when we are looking at a long line of charges like this that looks like a cylinder, right, the electric field has to have symmetry that matches it. So if we spin it around, it has to look the same. If I reflect it about the axis, it's got to look the same. Right, so the electric field has to match the symmetry of the charge. And then same thing for a point charge, right? A point has spherical symmetry, and the electric field should also have spherical symmetry. So these are just a couple of examples to show you like how a field does not reflect the symmetry. Right, so for example, if we thought maybe for a big long line of charge, we thought the electric field should look like this with these vectors angled, have some angle, and then we reflect it around this plane, we don't get the same thing, right? We see that the electric field has changed. So again, this is wrong. This is just showing you a case where the field would not be reflecting the symmetry of the charge. And same thing from here. If we thought there was some weird spirally pattern of the electric field due to a point charge and we reflect it around the center, we get a different field. And so that doesn't work, right? So the field has to reflect the symmetry of the charge. So common types of symmetry that we have are a plane of charge, right? The electric field will be coming up and down perpendicular to the plane. It's planar symmetry. We have cylindrical symmetry, and again, the field lines will be coming perpendicular to the length of the cylinder. And then for spherical symmetry, right, we can rotate it around any angle and it should look the same. Rotate it about its center, through any angle and it should look the same. Okay, so when we are applying Gauss's law, we want to pick the surface, right? So Gauss's law again is saying that the charge the flux flowing through a closed surface is equal to the amount of charge enclosed. So we need to pick our surface to reflect the symmetry of the charge distribution. So if we had a point or a sphere of charge, we would pick a sphere as our surface. And remember that the surface area of the sphere is 4 pi r squared. If we had an infinite line or a wire or something like that it looks like a cylinder, then we pick a cylinder as our surface, and the area for that is 2 pi r, the radius of our surface times the length. And then if you have a plane of charge, that's a planar symmetry, and then we would pick a surface that's like a box that kind of goes above and below the surface, sometimes called a Gaussian pillbox, depending if you want to make it circular or square. Okay, so when we pick, the beauty of this is when we pick the right surface, we're picking it such that the electric field is constant along that surface, and then our integral becomes really easy. It's just the integral of the area. Okay, so again, when we choose a surface so that the electric field is constant and perpendicular to the surface, then the integral just simplifies. So this dot product just goes to 1. Electric field, it's be constant, so that can come outside the integral. And then we're just left with the integral of the area. Integral of the area element, which just gives us the area. Okay, so again, if you had some kind of sphere of charge, you would be picking the Gaussian surface of a sphere, and then you can just look in detail, right, where the area element and the electric field are pointing at every position, right? They're always parallel to each other. Okay, so just a note, right? So here I'm saying that the surface is perpendicular to the electric field, but the area vector will be parallel. Okay, so again, here is, like a line of charge, or it could be a wire or whatever, right? Here's our little area element. It's perpendicular to the field. The area vector is parallel to the field. And again, for the surface, so if you had an infinite plane of charge, this is kind of like a Gaussian pillbox, or like like you think of a cylinder basically that's cutting through the plane that you use for your surface. Okay, so let's just do one example of what if we want to calculate the electric field a certain distance from a point charge. Okay, so we have a charge plus Q, and we want to know what the electric field is a certain distance r away. Okay, and so we have a little sphere of charge. We are going to, or it could be a point charge, doesn't really matter, but our Gaussian surface is going to be a sphere. Okay, so we're going to use Gauss's law, right, that says the integral around this surface, and you got to imagine that this is like a 3D surface, right? So it's not just a circle that I'm drawing, it's a sphere. So the integral of the electric field around that area is going to be the enclosed charge over epsilon naught, and this is just a constant. Okay, so we're picking, we know that the electric field looks like this, right? And so just by symmetry, we know that it's got to be constant along this sphere. Oh, just one more. We block some of the outside light. Okay, so all along this sphere, the electric field is constant. Okay, and that's the surface that we're using. So, and that's just a symmetry argument, right? That we know it doesn't matter which way we rotate this charge, the field should look the same. So that means I can, and then also, let's look at one little element here, right? My electric field is going this way, and my area element dA is going that way too, right? So that means theta equals 0, and cosine of theta equals 1. So first thing, let's just break this out, right? So that means inside that integral, e dot dA, if we just do that here, dot dA is e times dA times the cosine of the angle between them. Okay, and we said when they are parallel, theta is 0, cosine is 1. Okay, so then inside my closed integral, now I have e dA, just the magnitude of those. And again, we just bring this down on the left side. That's the enclosed charge divided by epsilon naught. Okay, and now we said by symmetry, I picked a surface where my electric field is constant. So this comes outside of the integral now. So it's E times the integral of dA around that closed surface, and that's going to give me the enclosed charge over epsilon naught. Okay, well, we did this already, right? We didn't actually do out the calculus, but we know if I take all my little area elements and sum them all around the sphere, I'm going to get the surface area of the sphere. So that's 4 pi r squared. And then again, on the left, I have Q enclosed over epsilon naught. Okay, and now we're just going to solve for the field. So we're dividing by 4 pi r squared. So we get the electric field at some radius r is Q enclosed. So I can replace that now. That was my plus Q. Let me get a big Q over 4 pi epsilon naught r squared. Okay, and so remember this K is 1 over 4 pi epsilon naught. So the electric field is exactly what we had gotten used before, although we never actually said where it comes from, right? That it's KQ over r squared. But we can leave it in this form as well, right? It's equivalent. So Q over 4 pi epsilon naught r squared. Or if we bring that out, right? 1 over 4 pi epsilon naught Q over r squared. So that's it. So that's mostly how it's going to go, right? So we're picking a surface where the area vector and the electric field are parallel. So the dot product just becomes the magnitude of the electric field times the magnitude of the area element. Let's focus here. Sorry if it's been out of focus the whole time. Okay, so we're picking an area where the area vector and the electric field are parallel, right? So theta is 0, cosine of theta is 1. The dot product of E dot dA just becomes the magnitude of the electric field times the magnitude of the area element. And we're also picking a surface where the electric field is constant, right? So this first part changes our integral to this, gets rid of the dot product kind of collapses. And then since we picked a surface where the electric field is constant, electric field pops outside of the integral, and then we're just integrating the area. And in practice, we're picking surfaces usually where we know the area, so we don't actually need to do that integral. And in this case, we just know the surface area of the sphere is 4 pi r squared, and then we can get E by itself to get the relationship for the electric field.